In this video, we will solve this mobile unlock patterns problem. So let's see the problem. So the problem says that there is a 3x3 grid in a mobile screen. If you have any Android mobile phone, you must have used some pattern to unlock your phone. Maybe like this or some custom pattern. So that is generally a 3x3 grid and you have to draw the pattern over there. And given the length of the pattern, you have to find the number of different patterns you can make. So you have to define a function num patterns where we have two values m and n. So m is the length of pattern, minimum length of pattern, n is the maximum length. So you have to find all the patterns with the length of m, m plus 1, m plus 2 all the way up to n. So here we have 3x3 grid, so we can represent them by numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. And the condition is that when you draw a pattern, let's say this pattern, then all the numbers, all the digits on the sequence, so pattern is a sequence of digits here, if you represent each value by a number, should be unique. All the digits should be unique. So for example, 1, 2, 3, 6, 5. So let's say this is the pattern 1, 2, 3, 6, 5. This is a valid pattern. But if we write 1, 2, 3, 6, 5 and again we write 2, it's not valid since 2 is occurring twice. Also, there are a few more conditions that in this sequence, so we are moving from left to right. So 1 is the first value, so we are here. So let me redraw it, the same pattern. So first we are at 1. Let's draw in the center. Then we go to 2. So this is a valid move since 2 is adjacent to 1. Similarly, from 2 to 3, it's a valid move. 3 to 6, it's a valid move. 6 to 5 again valid. But if we have some pattern, let's say 1, 2, then 8. Let's see this small cases so that it's easy to understand. So if it's 1 to 8, we come from 1 to 2, it's a valid move. From 2, we cannot go to 8 directly. We have to go through 5. So if this is the case, we are jumping some value that is occurring in the middle. Then the condition is that that is even allowed, but under certain condition. So that is allowed only if this the value that we jumped is already visited. So if we are jumping any value, that must be visited. So either we are going to the neighbor, or if we are going through the center of any cell, then that should be visited. So in this case 1 to 8 is not allowed. Let's see a case where this kind of thing is allowed. So let's try to go from 1 to 2 and then 5, let's say, and 6 and 3. So we are going 1, 2, 5 this way. So understanding the problem is very important and the conditions of the problem. 1, 2, 5, 6, 3, and now we are going to 7. 3 to 7. So again you see that we jumped this value 5, but 5 was already visited. We came, 5 is already here, it's visited. So this is allowed, this is valid. Since there is no duplicate and when we are always going to either its neighbor or whenever we are jumping any value, then it's already visited. Now let's write a similar example. We from 1 to 2, 2 to 5, 5 to 6, 6 to 3, and then we are coming to 8. So this is not called a jump. We are going from this 5. So if you see, we are touching this cell 5 as well as 6 here. But these will not be counted. So it should go from the center. So you can think of it like these circles. So when we are coming from 3 to 8, this was 3 and this is 8. So if we are coming here, we are not touching any other circle. So this is not considered a jump. So this is fine. So this is the thing that I wanted to explain here. So this, it's called jump only if we are coming from here, like from the center. Same way here or this way. These are jumps. What is not jump? If we go from here to here, it's not a jump, or vice versa. If you draw in this grid format, it may seem that we are touching this 5 and 6, but that's not the case. It should go from the center. Now we have to implement this num patterns function with m and n. For example, if let's say the value is num patterns 1 and 1, that is only of length 1, then each digit itself is a pattern. 1 is a pattern, 2 is a pattern, so there will be 9. If we have, let's say, num 1 2, then we have to list all the patterns of length 1 and all the patterns of length 2. So patterns of length 1 will be these digits 1 to 9. Patterns of length 2 will be this 1 2. Similarly 2 3. 1 3 is not valid, it goes through 2 and it's not visited. Similarly, all the valid patterns of length 2. So we have to add those and return the value. Similarly for 3 and 4. So now let's see that if we have, so how we will approach this problem. So let's see. So we have this grid and you can write the values 1 2 3. So let's say we are finding the patterns of length 4. So from here we can go 2 3 4. Similarly other pattern of length 3 would be length 4 would be this. So first pattern is 1 2 3 4, 1 2 3 4 5 6, 1 2 3 6, and this one is 1 5 9, and many more patterns. Like this way, you can come here and here, you can come here and here. So all the patterns of length 4. So one thing you will notice is that either you start from this corner. Let's say if you start from this corner, there are 10 different patterns that you form, valid patterns of length 4. So there is nothing special about this corner. If you had started from here, you would have got the same number of patterns. Similarly from this corner, so this 1, this is 3. If you look at the corners, you have 1 3 7 9. These are symmetrical cases. So if you list down all the valid patterns from this 1, then you can list the same number will be valid for 3 and then 7. So 1 3 7 and 9. These are symmetrical cases. Similarly, if you start from this any of these middle values, so if you start from this value and you list down all the patterns, then whether you start from this cell or here or this one or this one, you will get exact same number. There is nothing special about this particular cell. These are all symmetrical, just the way these are symmetrical. So you can find the number of patterns starting from this digit 1 and this was 2 and multiply by 4. Similarly, you can count the number of valid patterns of the given length starting from this cell 2 and multiply by 4. So you have covered 8 out of 9 values. So one thing you would have to do for 5 separately. So number of patterns starting with 5 multiplied by 1. So these will be the total number of patterns of a given length. Number of patterns of a given length, let's say k. And you have to do for all the lengths from m to n. So all the patterns of length m, all the patterns of length m plus 1, all the way up to all the patterns of length n plus 1. So I hope you understood this problem well, and how you can reduce your calculation by taking the symmetric cases. So you just need to find these values. Patterns starting with letter 1 or this position, patterns starting with letter this, and you can multiply by 4 to cover other cases, and patterns starting from center. So how we will find a pattern of a given length starting with certain value. So we have this grid, 3 cross 3 grid. So let's say we are trying to find a pattern of length 4, and we are starting with this position. Current position is 1. So we can write a function, or num patterns in our case. So we have to pass the current position, that is this, let's say 1, and the remaining length. So this is the length of pattern, that is 4 minus 1. Since 1 is already included now, so we have to find the next 3 values. So first value is 1, next 3 values we don't. We have to list all the valid values filling these 3 places. So now it's 3. And we have to also keep track of visited. So first thing is that if we are going to one of the neighbors, then we don't need this to check this visited value. But if we are skipping some value, so if the initial cell was I, final cell was j, final value. So if we are jumping any value in between or not, if we are jumping, better that value be visited. If this is j and this is, let's say, k. So going from I to k, we will not check if it's visited. Any value is not jumped. If we are going from I to j, we will check whether this jumped value is visited or not. And then we have to list all the values. So we will try for all the values. This part, all the 9 values in fact. From 1 you can even try this. It's valid. From 1 we can directly go to 9. So 1, 9 may be a valid value provided this 5 was visited. So for all the values from 1 to 9, we will check if by placing the next value this sequence remains valid or not, and we have to list all those values. So first we will list 2 and then call this function recursively with the length of 2 because 2 places are remaining. Then from 2 again, so it's like doing a DFS. We are at some starting node, we take the next neighbor. In this case, all the cell values other than the current one are its neighbors. And provided that if we are jumping, it's visited, then we have to check for all the 8 values. And again from next value, length is fixed. So length is decreasing, required length is decreasing by 1. And all these paths are of length 4. And then we are going back and looking at other possible values here. And when exhausted with this, we go back again and list out other possibilities. So we just need to keep track of count and nothing else. So now let's start the implementation of this. So this is a simple DFS with certain conditions of adjacency. So now let's write the code for this. So this is our code, and we have to define a function num patterns. M is the minimum length, n is the maximum length, and we will try it out on certain inputs to see if it's working or not. So first we have to keep track of this jump. So let's list down all the jump values. So in order to find the value that was jumped, we have to pass two values, the initial value and the final value, and these will lie in the range of 1 to 9, both of these indices. So we can create an array of size maybe 10 cross 10, that should suffice. And 0 is not part of this, let's say, then initially all are 0. Then we have to write mid lm. So when we go from 1 to 3 or 3 to 1, then we are jumping this 2 in between. We are going from 1 to 3 or 3 to 1. Similarly for other cases. So next, let's say we go from 1 to 7 or 7 to 1. We are skipping 4. Next we are going from 3 to 9 or 9 to 3. Then we are skipping 6. 3 to 9 or 9 to 3. Then 7 to 9 or 9 to 7. Seven to 9, 9 to 7. The skipped value is 8. Next 4 to 6 or 6 to 4, these horizontal values. 4 to 6, 6 to 4, 2 to 8, 8 to 2. The skipped value is 5 for all of these, and similarly for 3 to 7, 1 to 9. So all of these, the skipped value is 5. So we can write a big inequality here. So 1 to 9, 1 to 9, then 9 to 1, then 1 to 9, 9 to 1, 3 to 7, 7 to 3. Then we have 2 to 8, 4 to 6. For all of these, the jump value is 5. Next, we keep track of a visited list. So we are keeping track of visited for all the 9 values. And then count is initially 0 for int I equal to 0, or m is the minimum length, n is the maximum length. We have to try for all such lengths. count plus equal to dfs. So we will write a dfs function now, and we will start dfs from 1, and we will multiply by 4 for all the corners, then count dfs. We will start from 2 and multiply by 4. So we will fill these parameters when we define dfs, and then we have to do a separate dfs from center, that is 5. And finally we will return count. Now let's write our dfs function. So one of the values will be current value. Then we can have remaining length, and we also need this visited array. And this mid elements list, which we will use to check whether we jumped any element or not. If we jumped any element, then whether it's visited or not. So if remaining length is less than 0, then there is no combination possible. So return 0 if remaining length is equal to 0. Return 1 since we will not use any pattern, that is the only way. Otherwise standard DFS process. So visited of current. So this we are assuming numbers from 1 to 9, so this value will be 1 to 9, but index it's a 9 length, or you can keep length 10, 1 extra, nothing corresponding to 0. Then visited current equal to true, because index start from 0 and we have numbers from 1 to 9. So at index 0 we wanted to keep 1, but now we have 1 extra, so 0 will not be used. So visited current is true. This is standard DFS. Then count is 0, and then we have in standard DFS what we write. So this current is the current node. So we from current node we can only go to its neighbors, adjacent nodes. So we listed for all the adjacent nodes of this current. So in this case all the 9 values are possible, leaving the current value. For I equal to 1, I less than or equal to 9 plus I. So we have to do DFS. So if it's not visited, so this will automatically account for ignoring the current value. We don't need to check whether I is equal to current or not, because current we set to visited, so it will automatically ignore that case. So it should be not visited, and either mid elem from current. If we are going from current to this I, either mid element is 0, that is we did not jump any element, or visited. If we are jumping any value, then it should be visited. Then we will trigger a DFS. trigger DFS from this next node I, and the remaining length will be 1 less. And once this complete, we set visited back to 0 for next pattern. Now let's try to run it. Okay, so we did not update this. So the way to call is mid element visited current element, and remaining length is I minus 1. Since we have added this value 1, and we will multiply by 4, the same thing here. Starting from 2 and then starting from 5. Now it works. So for one length it shows 9, which is correct. For 5 to 7 it shows 106,080, which should hopefully be correct. You can check it. So the time complexity here would be the time taken for standard DFS, which will be order of number of vertices plus number of edges. In this case, number of vertices is 9, number of edges is some function of 9, so you can assume it to be constant. So if you did not understand it, you can go through it again. It's slightly on the tougher side, so you may not be able to solve it in one go. But if you are able to understand the pattern, you will see that it's a simple depth first search. You start from some value and you know the length of the path where we need to terminate. So you do DFS starting from all these nodes and you know the length of pattern. You have to define the adjacent nodes intelligently based on whether they are neighbors, or if you are jumping some value, that value should be already visited. So good luck. See you in the next video.